Hello everyone, my name is Yuanhui Zeng, and I will go over my ECE 5213 final project report. And the topic actually is about the brain-computer interface. And in my presentation, I will go over the brain-computer interface background, concepts development, engineering development stage, and post-development stage, system engineering challenge of the program, and summary and lessons learned. So in the background of the BSI system, I will talk about its history and now. In 1924, German physicist Hans Berger recorded the tiny vibration of the uh, galvanometer on the scalp of patient with a skull defect, recording brainwave for the first time, opening era of the academic exploration of brain-computer interface technology. In 1969 to 2009, researchers devised a game in which monkey connected neurons to a dashboard, and then reward the monkey with a banana by feeding back change in value of meter through the neuron. It was not until the uh, year of 1990s that people gradually applied the particle-based biases obtained from animal experiment to human. So today, the two well-known giants of brain-computer interface research are Facebook and Neuralink. Those existing brain-computer interface technology is only preliminary solution to the direct output and control of the brain computer. And the control efficiency and accuracy are still very low. As things stand, brain-computer interface technology is far from being practical on large scale. So the BCI technology has a wide range of application devices as input. Today, several companies and laboratories produce full-fledged brain-computer interface components. In my survey, the application of BCI technology in the following field is relatively mature and can meet the demand for new system. Rehabilitation, therapy, motor assistance, brain state monitoring, communication and interaction, entertainment, smart furniture, control, and recognition. So the rehabilitation therapy. Currently, the most widely used field of the EEG is neuroscience, especially neurotherapy such as neurofeedback training. Currently, there are some daily products on the market for non-medical purposes, such as improved concentration, regulation mood, and electronic product to enhance the athletic potential of athletics. Since the brain neural system of those patients is normal, the brain-computer interface can be combined with exoskeletons and prosthetics, and external device can be directly controlled by electrical signal to assist the limbo to complete the desired movements. At the opening ceremony of the 2014 World Cup in Brazil, A young man with a high degree of pathology wear a magnetic exoskeleton and kicked the first ball with a brain-computer interface, showing the world the application value of the brain-computer interface as a tool for movement disordered. In non-medical field, monitoring the mental state of user is also promising application, such as monitoring the mental state of worker in dangerous work, such as miner and truck drivers, especially when the EEG is comboed with the device. It is very effective to monitoring and to warn an interview in time. And in the communication and interaction area, the most successful application is Speller, which is a phonetic spelling system based on the EEG P300 waves. The most famous example of the BCI speller is the speech assistant system used by Stephen Hawking. There are already many EEG-based BCI game software and hardware systems on the market, but due to their non-medical use, the really low accuracy and horrible varying design, those issues lead to low control accuracy and poor experience, which lead to brain control games. And the fundamental reason why the concept is very hot, but the actual market is not strong. The original design intent of the BCI smart furniture system is to enable the elder and disabled people with limited motivation to live independently in their daily life and simplify the way of life to the normal people. The function of brain-computer interface is only similar to that of the remote control, help people control doors and their other device with their brains. So next part is concept development. And in the concept exploration part, there are three uses of the BCI system. First one is invasive brain-computer interface, and partly invasive brain-computer interface. And the last one is non-invasive brain-computer interface. And let's see how they are different. An invasive BCI require surgically implanted electrode under the scalp to deliver brain signals, because the electrical signal can be read directly from the brain's gravimeter. This makes reading very accurate. However, the side effects after surgery are also harmful. Some bad issues may form after surgery, like weakening brain signals. Moreover, the patient's body will produce different degree of the rejection. Partially invasive BCI are implanted in the skull rather than in the gray matter of the brain. This allows to receive high-quality resolution signal with a low risk of the bad issue formation in the brain compared to the invasive BCI. Some of the current cutting-edge projects are still exploring less invasive implantation approaches, such as EEG or ECG. Those those implant masks to not require open brain surgery. And non-invasive BCI are the most mainstream and widely used brain-computer interface today. This form is easy to wear and requires no surgery at all, and user methods such as EEG and EOG to collect electrical signal and generate feedback on them. But non-invasive BCI cannot effectively pick up high-frequency signal because the school suppresses the signals, scattering and obscuring the electromagnetic wave produced by the neurons. Therefore, in the planning of this project, I hope to focus on some non-invasive brain-computer interface and particle invasive computer interface, because the current invasive computer interface technology is immature and risk is really high. It may cause can't predictable harm for the human's brain, and there are ethical issues at the same time. Next is about the concept development of the concept definition part. So in this part, EEG is one of the main information analysis techniques for non-invasive brain-computer interface and has great potential, mainly because of its good temporal resolution, portability, and relative low price. The most commonly used cranial nervous signal in brain-computer interface research are P300 evoked potentials. P300 is an event-related potentials. The positive potentials are paired 300 to 400 millimeters after time-related simulation, were mainly located in the central cortex, and their peak appeared about 300 millimeters after time. EEG signal, BCI input signal, has its own character and limitations. Both P300 and visual evoked potential are evoked do not require training, so their signal detection and processing methods are relatively simple and have high precision. The disadvantage is that the additional stimulation devices are required to provide the stimulation, and it depends on center human participation such as sight and hearing. And in this part, I have the engineering development stage of the advanced development phases. So this validates component and subsystem design concepts at the low cost through the experimentation to advanced development stage and open the way for subsequent product development in the future. This part is one of the most important phases in the whole system design. So the advanced development phase is devoted to designing and demonst- demonstrating and develop the part of the system. And the main purpose of this phase is to define and reduce the development risk. During these phases, system engineers are able to measure progress, evaluate and select alternatives, and document decisions made during the developments. System engineers consider a wide range of metrics, such as cost, technical qualifications, and interface parameters, to help teams make decisions that ultimately lead to the most successful projects. In the early days of project development, the only thing scientists can rely on is animal testing, and the technical can then be further tested. Developer can start trying to design a brain-computer interface system based on viral invoked potentials. These validate components are subsystem design concepts at the lowest cost through experimentation at advanced development stage and open the way for subsequent product development. And next, we have the engineering design phase. This part can set a valid and achievable goal for brain-computer interface system project before putting a lot of effort into developing it. And in the engineering design phase, after completing the requirements analysis and direction of the concept, what is done is planning the necessary work and activities required to executing the system engineering process, as well as scheduling and cost estimation. The hardware layer is further divided into EEG acquisition equipment and external control equipment. EEG acquisition equipment includes core component and device, electrodes, chips, power supplies, and some other materials. And the software layers include biosignal analysis and deep learning algorithm, communication computing, and security provising. Brain research is also an important aspect of software stimulation and implementation. So it's a huge work to combine this together to make a design and to allow the protocol of those different parts to fit each different device. And next, we are going to the integration and evaluation phase. In this phase, experienced system engineers know how to utilize different verification methods to simplify the verification process by properly dividing design and verification activities. System engineer can minimize error, include the retesting. So in the integration and evaluation phase, the most important thing is to integrate the engineering component of the complex system into a functional whole and to evaluate the operation of the system in the real environment. Once the other part is integrated, the verification process mm, validation is the process of evaluating a completed design. For design verification uses a traceable and targetable approach. And on my next stage is about the post-development stage. And this stage was about producting phase and operation and support phase. So let's see what's in it. The development of modern medical device presents many complex challenges. A brain-computer interface as a medical device provides coordination and overall guidance between different engineering disciplines at every stage of development project. The use of system engineering techniques and process in S-Node to remain competitive and relevant in today's marketplace. During this phase, product design and manufacturing engineering team work closely with project leader to manage the technical work of the product from the development team to the factory. The most successful project also will stay in close contact with the stakeholder throughout the product development process. This means regular engagement with customer, user, operator, technicians, and other relevant stakeholders. And next one is the operation and support phase. So typically, developer also document any and all change to this artifact for version control. Ensuring the project has traceable steps throughout the process helps everyone stay on the top of change detail training of system. Operation and maintenance staff is also critical. The training content should cover a full range of technical textbook knowledge and practical experience training. And in the system engineering challenge of the program, first, there is the quality of the occurring signal. It's the most important challenge. Since the EEG signal itself is very weak at the microvolt level, it is easily affected by various noise. Even in very expensive and high-precision EEG research equipment, users often require a resting state. So in terms of application, very simple and preliminary commercial product can be realized. But if you want to really control a machine as you can imaging, such as robotic arm that can replace with your own arm and achieve true autonomous control. There is still a long way to go. Will brain-computer interface technology creates a new opportunity for the development of human technologies. It also brings a new security risk and ethical challenge. The first is safety risk surgery. Implantable electrode need to be surgically implanted, which involve heightened danger in surgery safety. Neural activation may alter brain state, affecting people's mood, autonomy, and personality, among other things. Uh, as a comprehensive field, brain-computer interface research needs talent from various related fields to make progress together. The price is high, and things like lower cost require more researcher to work with lab. So this is a business opportunity. It is believed that driven by the market and demanded, the cost of equipment will be further reduced and more developer will devote themselves to the work of BCI equipment. That's it for the challenge of the program we are facing now. So, unlike academia, commercial companies tend to focus on engineering, and the academia usually focus on some theory of a new technology, and they have a lot of, and the commercial companies usually have lots of manpower and foundations, which is a completely different mode compared with the laboratory. And the culture's approach of scientists often lead to slow progress in results. There are usually dozens of people in laboratory to study a topic, and funds are relatively limited. Some analysts predict that by 2030, the global BCI market value will reach to 534 billion US dollars from global companies investing in brain science research, such as Neuralink and Facebook, and other large companies work to development brain-computer interface devices that are widely used by patients and ordinary customers. The application prospects of BCI technologies are endless. So combine the laboratory and commercial companies. That will really improve the effective of pushing the BCI technology in the future. And here is some reference I used. I use those information from the website such Wikipedia, some news report, and ECE and papers. And that's all for my presentation. So thank you for watching and have a good day.